The next constructions that we want to look at now play on a single space X, but generalize some concepts from commutative algebra that we know about modules. More concretely, if R is a ring and M and N are R modules, and you have a R module homomorphism between them, then we know that we can form the kernel, which is a submodule of M, and the image, which is a submodule of N, and both of them are, again, R modules. And the question is, how do you generalize this to now a morphism of sheaves of modules or of OX modules living on a single space? And it turns out one of the constructions is relatively straightforward, namely the kernel. So if you have a morphism of sheaves on some scheme X, then you can, so this is F, and you can form the kernel of F, which just takes values on an open set U to be the kernel of the corresponding morphism of OU modules. Okay, so this is straightforward. The data of F contains all of these morphisms here, and you just take the kernel. This is, of course, again, an OU module, because F of U was. And so, first of all, we see it is a presheaf with the restrictions coming from the sheaf F. And to see this, well, assume you have phi in the kernel of Fu on some bigger set U, and then you have a subset V. Then we want to show the restriction of phi to V is still in the kernel. So we want that if you restrict and then apply the Fv, then you get 0. But now we just use, well, everything, all these data is compatible with restrictions. In particular, we can first apply Fu and then restrict. This gives the same thing. But phi was in the kernel of Fu. So this thing is just 0. And then we use that the restriction operation is a morphism of modules in the sense that we discussed before. So it must send 0 to 0. Okay. So this thing is 0. And so indeed, phi restricted to V is in the kernel as desired. This shows the restriction maps that we now defined make it a presheaf, but it's also a sheaf. So, so for this, we will have to use that both the domain and the target are both sheaves themselves. We use this at 2 different points. So what we need to check for being a sheaf is that if we have any open cover of some open set U, and we have sections of this kernel sheaf on each of the elements of the cover, on each of the UI, which are compatible on the overlaps here, then they glue together to a section of the kernel sheaf on U. And so the first thing that we use is that F itself is a sheaf, because in particular, all these phi I are also sections of F on all of these UI, and they're compatible. So by the sheaf property of F, they glue together to unique phi in F of U, which has this nice restriction property. So this basically already shows the uniqueness. And now for the existence part, we need to check that this phi is actually also in the kernel section of the kernel sheaf, not just a section of F. So what we need to do is we need to show that if you apply F of U to phi, then you get a section psi of G on U, and we want to show that psi is 0. That would mean that, that the phi was in the kernel. So we know, what do we know about this psi? Well, we know it satisfies that on the open subsets of the cover on the UI, it is just given by somehow, now again, we use this kind of restriction commutes with the map. So somehow it is given by first restricting phi to UI and then applying this. But this here was phi I was in the kernel sheaf, and so this is 0. So we got a section of G, which on this open cover, if you restrict it to any part of the open cover, vanishes. And now we use that G is a sheaf and see that the only section of G which can restrict to 0 on all the parts must actually be the 0 section. It's the unique one which has this property. And so phi is in the kernel here. So you see for the basically for the uniqueness part, we used that f is a sheaf, and then for the existence part, making sure that what we got is actually in the kernel, we used the fact that G is a sheaf. And so this ker f is called the kernel sheaf of this morphism of sheaves. And the idea here is that why did we get a sheaf again? Well, the answer is just that being in this kernel can be checked locally on U. This is a property which can be checked just on some open cover, for example, as we did here. Now, so this worked out very well. So we hope that maybe for the image, it will work just the same, but unfortunately, this will not quite be true. So, but we let's just go ahead and see what happens if we try to basically copy paste the definition from above. So again, you have f, this morphism, and then we define an image presheaf. And we indicate this by denoting it by im prime of f. But the definition would just be as above. We take the image of this restriction, of this restricted morphism here. This is called the image presheaf, and it has a presheaf structure with the restrictions coming from G. And the presheaf part is actually not a problem, because if you have psi given by fu of phi in the image presheaf, so in other words, in the image of this fu, then for any open subset V inside U, well, we just do the exact same trick. So we start with fv of the restriction. This is the same thing as fu of the big thing, and then restrict. Fu, by definition, is psi. And then what we see here is that if we restrict psi to V, then it is again in the image of fv. This is what we just showed. And so this means if you have a section of this image presheaf, you restrict it, you again have a section of the image presheaf. This part worked fine. But now the problem is this thing is not a sheaf in general. So even if f and g are sheaves, this will not necessarily be a sheaf. And the idea why this fails is that if you have an open cover of some U, and you know that you have sections of this image presheaf on each part. So you have this psi I given by fui of phi I on each of these parts. The problem is now we would like to say, well, then we glue together the phi I, getting some big, phi which maps to the psi, giving the section on all of you. But the problem is those phi I don't have to glue together to some section here. And the issue is just we know that the psi i's agree on overlaps, but this doesn't mean that these pre-images phi I have to agree. I mean, if all of these things are injective, then you can kind of conclude this, but in general, this will not be the case. So now this looks like a kind of abstract problem. It looks like, okay, the standard proof that we would like to write down is not correct, but maybe it could still be that the statement is correct. But unfortunately, there is a concrete counterexample. And I mean, it's not super hard to write down, but we do have to fill in a short table to see it. So to get this counterexample, we need to take a space X, and we need to have a morphism of sheaves on it. And in fact, we can take somehow X will basically be A2. And the morphism of sheaves that we want is a morphism induced by actually a map of schemes. So there is this kind of inclusion morphism from A1 to A2, which just sends x1 to x1, comma 0. This is what happens on the level of closed points, and then there's unique morphism of schemes which fits this. And then this morphism comes with the data, as we have seen last time. It comes with the data of a morphism from O of A2 to the push forward of O of A1. Right? This is the morphism on x equals A2 here. And then we want to show that this image presheaf doesn't satisfy the sheaf property. And so what this means is we need to find an open set U, and we need to find some cover of U with compatible sections of this image presheaf which don't glue to a section of the image presheaf on all of U. And what we do is we take U to be A2 minus the origin, like this. And this has this standard cover that we looked at many times by these two distinguished open sets where either of the two coordinates is not allowed to be 0. Okay. And so what we need to do to conclude here is we need to find what the sections of the image presheaf are on these different sets. And so let's try to fill out this table. So here you see some open subsets of U. So this U1, U2, their intersection, and then also their union. And let's start to fill out what the different sheaves involved above have as sections there. So O of A2 on V, this is pretty simple. We have actually calculated this ourselves in all of these cases. So for example, on this distinguished open set, the regular functions that are allowed is exactly, we are allowed to have a polynomial in the two variables. And then because we remove the locus where x1 is 0, we localize exactly at this element. And similarly for U2, we localize at x2. And then their intersection, well, the intersection is if you remove both of these parts, this is the distinguished open set for x1 times x2. And so the sections are just given by localizing again at this element. And then maybe the most interesting part of this table, or of this column at least, is what are the sections, what are the regular functions on this here. And this was one of the big exercises that we had, or the big statements, that regular function here actually is the restriction of just a polynomial. So it must come from global polynomial. And this entry here will be the reason why this example works and why this example gives a counterexample. Okay, so this was the thing here. And now, I mean, we need to calculate these because we need to calculate the images of this thing on different open sets to get this image presheaf here. So now let's compute what the target does. And so we need to see what this push forward sheaf does on V. Okay, and the first one is not so terrible. So somehow now we look at this map, and the open set that we take is U1, which is this kind of complement of this this y-axis here. So we take the complement of the y-axis here, and then to compute what the push forward does is we just take the pre-image in A1, and then removing this line here, if you take the pre-image, just removes the single point. So we get the regular functions on, so this push forward on this open set here, by definition, is O of A1 on the pre-image. The pre-image is just a complement of the origin. So we want to know just what are the regular functions on A1 minus the origin. Well, this we know. It's again a distinguished open set. Is given by k of x1 localized at x1. The next thing is, if we take u2, then we remove the entire x-axis, and then we take the pre-image. But then the pre-image is empty, because none of the points here map to anything away from the x-axis. So the pre-image is empty, and so actually we just get 0 here. And then if we go to an even smaller set, if we intersect u1 with u2, well, the pre-image is still empty, so we still get just 0. And then finally, what happens if we take the pre-image of A2 minus the origin under this map? Well, then again, we just kind of remove the origin here. And then we get the same sections as for U1. We just allow some pole at the origin, like this. Okay, so now we have calculated for each of these open sets what this sheaf does on the open set, what this sheaf does on the open set. So now we write down what the image is. So somehow we look at this space. This has a natural map to this space here. The map will always just be set x1, set x2 to be 0. And then we see what is the image. Well, setting x2 to be 0, this just becomes the map from kx1 localized at x1 to itself. So the image is everything. So we just get all of this. In these two cases, well, the target space is already 0. And so the image of this map will also have to be 0. So we just get 0 and 0. And then again, kind of the interesting part here is that we have a map from here to there, setting x2 to be 0. And this map is not surjective, right? Because we don't allow, on this side, we don't allow dividing by x1. So the image of this map in here, well, you just set x2 to be 0, so it's just the image of k of x1 inside this localization. There's an injective map, so you just get k of x1. Like this. So now we know precisely what this image presheaf does on all of these open sets. And why did we fill out these tables? Like how do we now get the counterexample? Well, we write down two sections of this im prime on these two parts, which agree on overlaps, but which don't glue together to a global section. And the thing that we just do is, so we write down elements here and here, which map to the same thing here by restricting, but which don't glue to something in here. And so these spaces are now all very simple. We can just take, for example, 1 over x1. This is a section on u1. This is an element here. So it's an im prime f of u1. And then the other section where we don't have much choice, we just take 0 in im prime f of u2. They are compatible on u1 intersected u2 because, well, both of these spaces by restriction map to the 0 space, but of course the two elements just must map to the same 0 element. So they are compatible on the overlaps, but they don't glue on U, because there's no element in k of x1 which maps to 1 over x1 on here. And so this is a concrete example showing that this image presheaf is not a sheaf. And this will force us to think a bit about the situation, like what if you have something which already is a presheaf and it has a nice module structure, but it's not a sheaf. So this is a situation which we have to repair in a certain sense. We have to modify this presheaf, go to a new constructed sheaf from this, which actually has this sheaf axiom. And so this is something that we're going to do in some of the following videos.